lesson for 7.2 Antidifferentiation by Substitution. So this lesson is going to dive more into the indefinite integral, which was introduced in 7.1. So this would be the family of all antiderivatives of some function, or of a function, is the indefinite integral of f with respect to x, and it is denoted as follows. So you have the integral symbol, that's that stretched out s looking thing, and then of f of x dx. Now the dx, that's the differential there. That's just denoting what we are taking the antiderivative with respect to. So x is going to be like the key variable in our equation. So we're going to start off with example 1, looking at an easy example of this. And then we're going to get more into the substitution aspect, and I'm going to show you how to work with things whenever you can't quite tell what the antiderivative would be. So first we have a little bit more information here. If capital F is any function such that f prime of x is equal to f of x, then your integral of f of x dx is equal to f of x plus c, where c is some arbitrary constant that's called your constant of integration. And again, we use that plus c in 7.1. Definite integral is where you get a number. So that's what we did mainly in chapter 6. Indefinite integral is going to be that family of functions that have the common derivative. So here's our first one that we're going to evaluate. There are no bounds. If there were bounds on our integral, you would see numbers at the bottom and at the top here. And notice those are not zeros. I circled the fact that there's nothing there. So that's a big indication that this is an indefinite integral. So now we are going to take the antiderivative of both pieces. The antiderivative of x squared is 1/3 x cubed. So we add 1 to the exponent and then divide by the new exponent. And you'll actually see more about that coming up here very shortly. And then minus sine of x, the derivative that would give us, or the function that would give us a derivative of minus sine is plus cosine. And then we would put the plus c on the end. So you can go back through and take the derivative here and make sure that you get what you started with. It doesn't give us any initial point or point that the function has to pass through, so there's no way to find c. So this would be our correct answer there. So that's what we've kind of already worked with in 7.1, but that's not always going to be something that works out the way that you think it should. And so in your textbook, there is a page with various indefinite integral properties and formulas. And I believe this is on page 337 in your textbook. I did upload this document into Schoology, so it's just a scanned thing from the page, so you can see what those different properties are. So it goes through the fact that if you have a constant times a function, you can pull that constant out of the integral. If you have the integral of two functions that are being added or subtracted, you can find the integral of each piece separately and then add or subtract depending on your sign, which is actually what we did in example 1. The power formula, so how to undo the power formula. The rule for natural log, because again, remember the derivative of natural log is 1 over x. So if you're taking the integral of 1 over x, you would end up with natural log. The trig formulas, they're there, and then some of the exponential and logarithm formulas are on there as well. This is something that you may want to actually copy down or at least print out and maybe glue into your notes or staple into your notes, because it is extremely important that you do know those antidifferentiation formulas. So example 2, we're actually going to verify 2 of the formulas. One of them is going to be the natural log formula, and the other one is the u natural log u minus u formula. So we're going to verify this by actually taking the derivative. So I'm going to take the derivative of the natural log of the absolute value of u plus c. You do have to note here that u would have to be greater than 0. I know the natural log of u does have the absolute value around it, but because the derivative here is 1 over u, because we have this is greater than or equal to 0, I don't need to put absolute values around that. So that's just equal to 1 over u, so that one checks out. Now your second formula is a little bit different. So again, I am doing the derivative of this side here. Well, u natural log u, I have to use the product rule on that. So that would be the first times the derivative of the second plus the second times the derivative of the first. And then the derivative of minus u is minus 1. Derivative of c is 0. U times 1 over u is 1. So I have 1 plus natural log u minus 1, and then the 0 drops off. We're just left with natural log u, and that checks out to what we had in our integral in the beginning. So that's some verification. You do need to be, well, here's some other background around the differential dx. That has to do with the connection to the Riemann sum formula, which you can see there. So the dx, the delta x, that's basically the width there. It does seem unnecessary, but it is useful, especially when you are looking at the effects where the chain rule is involved. And that's what you're going to see in example 3. Because if it had been something different than dx, like du or dy, we may not be able to work with it exactly the same way, depending on what variables I have in my function. So this is example 3. It tells us that f of x is x cubed plus 1, and u is equal to x squared. And at first glance, all 3 of these integrals look the same. But if you look closer, part A is f of x dx, so that's the antiderivative with respect to x. Part B is f of u du, so that would be the antiderivative of the u function with respect to u. And then C is f of u dx, so you're using a u function, but you're taking the antiderivative with respect to x. And you'll see all 3 of these are actually going to give us very different answers. So the first one is the most straightforward. This is the integral of x cubed plus 1, and then with respect to x, with that dx. So antiderivative formula is going to be 1/4 x to the 4th for the x cubed. Antiderivative of 1 is just x. And then we have a plus c on the end. And we're finished. Nothing else to do there. So the second one, it's f of u. So my function, I'm putting a u in everywhere there is a variable. And that's going to be u cubed plus 1 du. Now I know that u is equal to x squared, but I can't put the x squared in for the u yet. Otherwise, I'll have x's as my variables in the function, but u is my variable for my differential, and those wouldn't match. So you need to make sure that they match before you do your antiderivative. So with part B, I'm actually going to plug in the x squared after I take the antiderivative rather than before. So antiderivative of u cubed is 1/4 u to the 4th. Antiderivative of 1 is u, and then I have my plus c. Well, in order to compare these across the board, I do have to change the u's to x's. So this is going to be 1/4 x squared to the 4th plus x squared plus c. So we actually end up with 1/4 x to the 8th plus x squared plus c. Very different than what we got for the first answer for A. And you'll see part C is different yet. So this one is going to be the integral of u cubed plus 1 and then dx. Well, that's all well and good. However, I can't take the antiderivative with respect to x if I don't have any x's. So for part C, I actually have to change the u into an x before I do an antiderivative rather than waiting until after. Really, the d variable at the end, that is going to determine what variable everything else in the problem should be in terms of. So if there's a dx at the end, everything else is going to have to be in terms of x's. If there's a du at the end, like there was in part B, everything is going to have to be in terms of u. So u cubed, u is x squared, so x squared cubed is going to change to x to the 6th, and then of course the 1 can just stay 1. So the antiderivative here is 1/7 x to the 7th plus x, and then plus c. I can compare it across the board because everything is in terms of x, and you can see it is different still from the answer from A and the answer from B. This is something that can get a bit confusing unless you work with it quite a bit. I will try to link with some other Khan Academy videos and some other internet videos to help you with your understanding. This is just kind of a beginning part to understanding substitution. In example 4 and 5, we're going to dive further into that substitution method. Okay, so example 4, evaluate. I know it says evaluate, but we are still going to come up with some type of expression for our answer rather than an actual number value. The only time you're going to get a number value is if your integral does have numbers in the upper and lower bound positions. So we're evaluating sine of x times e to the cosine of x dx. When you're doing a substitution, because this does involve the product rules, the chain rule is involved, it might not always be obvious what your original function was to do something to find the antiderivative. That's why it's helpful to use the u substitution. There are some problems in your textbook where they will tell you what your u is going to equal, but then there's others where you have to come up with them on your own. Typically in a problem like this, unless you have multiple e terms, the whole e to whatever exponent is not going to be a u value. Typically your u value might be part of one of your trig functions. If you have a square root, it might be something that's in the square root. It's just something that might take a little bit of practice until you master the art of figuring out what terms make the better u substitutions here. So I need to let u be something here. My choices are sine of x and cosine of x. Keeping in mind that whatever I let u be, I'm going to take the derivative of that term, and that's going to be something dx. So I'm actually going to be replacing the dx with a du in my problem. That will allow me to take the antiderivative with respect to u because I'll no longer have any x's present. So I would suggest, because again, I need to make this so that it is as easy as possible to take the derivative. If I let the u be the cosine of x, that would make this term into e to the u power instead of e to the cosine of x power, and I can definitely do something with that. Plus, the derivative of cosine is negative sine of x. Well, I have a positive sine of x dx, so if I move that negative over and make negative du equal to sine of x dx, I can actually go through and do my substitution there. So I'm going to highlight what I'm substituting in. So the sine of x dx is going to change into a negative du, and the cosine of x is going to change into a u, and then the e is going to stay an e. So I could rearrange this and make this e of x, e to the cosine of x times sine of x dx to get them beside each other to do the negative du, but that's not necessary. You don't actually have to do it that way. So we have here e to the u times negative dx. Well, that negative is like a -1. I can shift that to in front of the e, and even further, I can shift that so that it's outside of the integral. And that's not a dx anymore, I'm sorry. That is a du. Which means I have negative integral e to the u du. Now I'm at a point where I can actually take the antiderivative. The negative will stay outside of my answer. The antiderivative of e to the u is e to the u. Again, don't forget your plus c. Once you've taken the antiderivative, you can go ahead and replace the u with what you'd originally had in the problem. So that's going to be negative e to the cosine of x plus c. So negative e to the cosine of x plus c. And you could check this by taking the derivative, and if you take the derivative, you would get sine of x times e to the cosine of x. The last one we're going to do in this particular video is example 5. This is another u substitution that we're going to go through and do. There are more examples in this section, but I'm going to hold off and do those in the second video just so these aren't quite as long. So when you have two terms, because we have x squared times this radical function here, you want to look and see where the bigger exponent of x is. And I can see I have my bigger exponent inside. So that is typically going to be what we let our u equal. So u is going to equal 5 plus 2x to the third power. Notice I did not include the square root with that, because if I took the derivative, not only would I have 1/2 times what's in the square root to the negative 1/2 power, and then I do the chain rule, and it just becomes a big old mess. And I don't have an additional square root in the denominator to deal with. So I can't include the square root because the derivative of the square root is not my problem, and that kind of defeats the whole purpose. However, when I take the derivative here, the derivative of 5 is 0, the derivative of 2x cubed is 6x squared dx, and while I don't have a 6x squared dx, I do have an x squared dx. So if I can get that x squared dx by itself, I can replace that with something. Because I have an x squared and I have a dx, and I can rearrange those in the problem. So to move this 6 over, that's going to be 1/6 du is equal to x squared dx. So just like we did before, I'm going to replace this inside part with my u. And then I'm going to replace the x squared dx with the 1/6 du. So my new problem is going to be the integral of the square root of u times 1/6 du. And then just like before, I can pull that 1/6 out. That's using one of the properties of indefinite integrals. That's whenever you have a constant, you can pull it out. You don't have to actually integrate with it inside. And so that's going to be square root of u du. Now, this might be a little bit difficult to think through. Remember, square root of u is u to the 1/2 power. This is just a product rule, or I'm sorry, a power rule. So I would add 1 to the exponent. So if you add 1 to 1/2, you get 3/2. And then you divide by the new exponent. So if you're dividing by 3/2, that's actually multiplying by 2/3. And then plus c. So now I can multiply the 1/6 and the 2/3 together. That is going to equal 1/9 u to the 3/2 power plus c. That's all the simplifying I can do. The only thing left to do is plug in the 5 plus 2x to the third for the u value. So this is 1/9 times 5 plus 2x to the third to the 3/2 power, and then plus c. So notice from the beginning it may not have been quite obvious what you needed to have. However, using the u substitution, it does aid you in solving this and being able to go through and take the derivative or antiderivative. Substitution is not a perfect method. It's not going to work in every case and all the time. There is an additional method called integration by parts, and if you take a calculus class in college, you will definitely see that. However, it is not on the AP exam, so that's one of the sections we actually skip in here. If you're interested in reading over that on your own, that is 7.3. You'll see that once we do 7.2, we're going to skip to 7.4, so again, it's not something we cover. But you can always go on and look at it on your own if that's something that you're interested in seeing. So go back and rewatch this video. There will be a part 2 video, so if you haven't already viewed that, make sure you go through and view that as well. And reach out to me if you have any questions.